In this video, we will discuss what is called the fundamental counting principle, and it allows us to count the number of ways we could perform a certain task if we can break it up into multiple independent steps. So we'll begin with the definition, and then we'll start applying this to various examples. So the definition begins by saying, consider a task that could be broken down into k consecutive steps. So here k is just representing any number that applies to that particular problem. And by consecutive steps, we means we could do the first thing, then the second thing, the third thing, so on and so forth. So in our example, we have step 1, step 2, all the way up to step k. And suppose for those individual k steps, we know that in order to accomplish step 1, that could be done in subscript 1 ways. So you knew exactly how many ways step 1 could occur. Similarly, you knew exactly how many ways step 2 could occur. We're calling that in sub 2 just for labeling purposes. So our subscript aligns with the step that we're on. All the way up to step k occurring in sub k ways. Here. Then the fundamental counting principle says if you know how each step would occur in so many ways, then the number of ways the entire process occurs is by multiplying together the amount of way each of the individual steps would occur. So the overall k-part task would occur in sub 1 times in sub 2 all the way up times in sub k. So the way I like to think about this particular rule is the number of ways an entire multi-step process could be accomplished is the number of ways each individual step occurs all multiplied together. So in our first example of this, we're asked how many ways is there to create a 2-digit number, and this 2-digit number that we're trying to create will be based on the digits 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then they give us this important clarification. Assume that we can repeat integers. So for instance, I could have the digit 1, 1. And for this particular chapter, we're going to use this phrase with repetition or without repetition so often that we will usually, instead of saying assume allow repeated integers, we'll just shorten that to with repetition. So look for that in future problems. So potentially I could begin this process by listing out all of the 2-digit numbers that are made up of the digits 1, 2, 3, 4, 5, 6, 7, 8, and 9, allowing repetition. But that would be a tedious process, and I'd have to be sure that I did it very carefully to make sure I didn't miss any digits. A more efficient way would be to realize that in order to count the number of 2-digit numbers, that's a 2-step process. The 2-step process is found by picking the first digit, so I'm just going to kind of make a little box here to help us visually focus. Pick the first digit. And after we pick the first digit, to finish up the process, we have to pick the second digit. So as we're working on this problem, do stay focused on the fact that this is just helping us organize our thoughts. There's nothing mathematical to these boxes or brackets. We just learned that the number of ways to do a multi-step task is the number of ways the individual steps occur multiplied together. So if I can figure out how many ways I could pick my first digit, and then I could figure out how many ways I could pick my second digit, then this rule tells me if I multiply those two things together, I will have solved the overall problem. So let's think about how many ways could I pick my first digit. It goes back to what digits am I allowed? I'm allowed to use 1, 2, 3, 4, 5, 6, 7, 8, or 9. That is 9 different options. So when I write this 9 here, I'm not saying I'm picking the digit 9, I'm saying there are 9 possibilities. The 9 possibilities are choosing either 1, 2, 3, 4, 5, 6, 7, 8, or 9. Now when it comes to picking my second digit, my reasoning here not only is based on what digits they allowed me to use, but if I'm allowed to repeat integers. So for instance, once I've picked the first digit, that choice is done. I've picked some number. And since it says I can allow repetition, that means I technically could choose the same digit again for the second place. So I don't have to eliminate any choices because it's okay if I repeat. So since I'm allowed to repeat, I still have 1, 2, 3, 4, 5, 6, 7, 8, 9 options. So I'm going to write another 9. Again, I'm not saying I'm picking 9. I'm saying there's 9 options here. And then to use this rule, it says if you multiply the number of ways each step could occur, that resulting value, which 9 times 9 is 81, means there's 81 ways to pick or to express with repetition. In our next example, we're asked how many ways is there to create, again, a 2-digit number. And here we're asked to use the digits 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then they add the caveat that we do not allow repeated integers, said more efficiently in future problems, without repetition. So since it said a 2-digit number, we can say this overall process, we want to think, how could I break it down into more workable, smaller chunks? So instead of picking the 2-digit number and figuring out how many ways that could occur, let's say, how many ways could I pick the first digit? And I use this brace as just a helpful visual reminder. And then after you pick the first digit in a 2-digit number, you have to then pick the second digit. So next comes picking the second digit number. And I know I need to figure out the number of ways that could occur. Okay. So for the first digit, you say I was allowed to use 1, 2, 3, 4, 5, 6, 7, 8, or 9. That's 9 different options. So I'm going to write down there's 9 ways I could pick the first digit. Again, keep in mind this is not saying I'm picking 9, I'm saying there's 9 ways. But once I've picked that first digit, let's say for instance as an example to think about this off to the side, let's say I picked 3 first. Based on what's highlighted in purple here, would I be allowed to choose 3 again for the second digit? Think about whether you'd answer yes or no there. If I've already picked 3 as the first digit, would I be allowed to pick 3 again as the second digit? No, that's not allowed because they said we could not repeat integers. So whatever we've picked for the first digit, it cannot occur again in the second digit because they said no repetition. Now, how do we take that idea and apply it to counting? Well, we don't actually know what digit I picked first. The whole part of this process is it's leaving it somewhat abstract. We're just counting the options. But whatever one of these digits that we picked first, there was 9 originally available to us. We've already used one of them here. So what we've done is we've said one of the things we can't use again. One of the 9 things cannot be used again because that would create repetition. So how many remaining options are there available to us? Only 8. Because we have to exclude the item that we used at the beginning, whichever one of those digits it occurred to be. And then finishing up this problem, once we've been able to break down the process into consecutive steps and figure out the number of ways each of those steps could occur, the number of ways the entire process occurs can be found by multiplying the number of ways the steps could occur separately together. And that would give us 72 ways to create a 2-digit number using the digits 1, 2, 3, 4, 5, 6, 7, 8, 9 without repetition. Contrast this with our previous example. You notice the previous example had the exact same setup, except for their difference here. The first example allowed repetition, and the second example said no repetition. The way those differences are expressed in the way we solve the problem is when we're allowed repetition, I still have all the original options available in the second step because I'm allowed to repeat. Whereas whenever we can't have repetition, I had to decrease the number of options available to me in the second step because I couldn't use whatever digit was chosen for the first digit. Originally, there were 9 options available in the first digit, but once you've picked your first digit, you now have 1 less, or 8 options available for the second digit. Next, we are asked to consider a club made of the individuals whose names are labeled A, B, C, D, E, shorthand for Alan, Bill, Kathy, David, and Evelyn. We are asked to consider in how many ways could this club elect a president and a secretary under the restrictions that no one may hold more than one office. This is a lengthy way in context of the problem to say without repetition. And additionally, we have the additional restriction that the secretary must be one of the males in the club. Now, for this particular problem, before we get started solving it, I'd like to highlight this useful problem-solving strategy to keep in mind in your future homework problems. Whenever one or more parts of the task has a special restriction, you should consider dealing with that special restriction before any of the other parts of the task. The more restrictions that are involved in one piece means you should deal with that first, and it's going to make the whole problem-solving process much easier. So it does matter what you focus on first. Now, with that in mind, what do you think is the extra restriction we have in this problem? Take a moment to read through it again if needed. The special restriction in this problem is that the secretary position cannot go to anybody in the club. There is a restriction based on how this problem's phrased that the secretary position must go to a man. Now, we were going to pick 2 positions. We're going to pick the president and we're going to pick the secretary. Take a moment to reread this example and ask yourself, are there any restrictions placed on the president? As we read through this example, we see there's no restrictions specifically placed on the president. However, anybody that I choose for the president cannot then be chosen as secretary because it says nobody can hold the same more than one office. So whoever we choose for one office can't be considered for the other office. Now, I know this is somewhat new to us, so it's going to take a bit of time to get in this frame of thought, but I'd encourage you to focus on it through this rest of this video. All of these problems involve seeing that this whole process, instead of thinking of it all together, which is complicated, I could break it down into pieces or consecutive decisions. Once I've broken it down into consecutive decisions, I can focus only on how many ways could I make this decision. Okay, then how many ways do I make the next decision? Once I know the number of ways I make each decision, our rule tells us that you can just multiply the number of ways each decision occurs, and that will give you the number of ways the whole task occurs. So for this particular problem, take a moment and think, how many decisions do I have to make to complete the problem? What would you describe them as? The first decision is picking what? The next decision is picking what? So since we're choosing somebody to be the president and somebody to be the secretary, I would say in general there's 2 different steps. Picking the president, picking the secretary. And I can do those in either order. I could pick the secretary first and then the president, or I could pick the president first and then the secretary. Now, in particular, we've learned the idea that if some position has extra restrictions, we should deal with that first. So what that means for us is we should pick the secretary's position first because it has the additional restrictions. So in order to help me visually kind of focus on what's going on, I like to draw these little brackets, and that helps me focus. This is this decision, and I always label what I'm looking at. So this is how many ways we can pick the secretary. Now, the only rule that we have to follow in picking the secretary is the secretary must be a man. Now, looking back at our club, Alan, Bill, Kathy, David, Evelyn, I see there's 3 candidates. Alan could be picked, Bill could be picked, David could be picked. So how many ways can we pick the secretary? Well, there's 3 people available who fit our criteria. So 3. Now we've picked the secretary. The next decision that comes to play is how many ways can we pick the president? Now, once we've chosen our secretary, we know it's one of the 3 men in the club, so it's either Alan, Bill, or David has been chosen as the secretary. How many people are now available to be chosen for president, keeping in mind that nobody can hold more than one office? As you think about this, take a minute or two to reread the problem, rephrase the question, pause the video and attempt it on your own, and then unpause to check your work. Again, your question is, you've already picked the secretary. It is one of the 3 men who are originally in the club. You know that one person cannot hold more than one office, so how many individuals remain to be picked for the position of president? So the idea is we had 3 men originally considered for the position of secretary. One of those men was picked for that position. So now, since nobody can hold 2 offices, that person who is picked for the secretary position cannot be considered again for the president's position. So now we have 2 men who could be considered for president. We don't know which 2, but all we have to know is the number of them, not particularly who it is. 2 men considered for president. Plus, now, since there's no gender restriction on the president's position, based on how this problem's worded, we can go back and say Kathy and Evelyn could also now be considered for president. So that adds 2 women. So altogether, there are 2 men in the running for president, along with 2 women in the running for president. That makes a total of 4 people in the running for president. Now, this process, they said pick a president, pick a secretary. We have outlined how many ways you could pick a secretary based on the restrictions of the problem. We've outlined how many ways we could pick a president based on the restrictions of the problem. And we know if you can figure out how many ways each individual step occurs, then you can figure out the total number of ways this could occur by multiplying the individual steps number of ways together, and that will give you the overall total number of ways this could occur. So there are 12 ways based on this club membership and these restrictions that we could pick a president and a secretary. Some states have license plates which have 3 letters followed by 3 digits. How many such license plates are possible? They then tell us the important piece of information that we are to assume that you can repeat digits or letters. Now, in these problems, in order to be successful, we need to say, okay, they're asking me how to do an entire process. We're not good at determining how many ways an entire process could occur. However, we are able to determine how many ways individual steps could occur. And then by the fundamental counting principle, we know that it's mathematically true that if you know the number of ways each step could occur, multiply all of those individual number of ways together, and you get the number of ways the entire process occurs. So looking at this process, picking license plates, as described, that have 3 letters followed by 3 digits, how many steps do you think or decisions are involved? Well, first up, we have to pick the letters. So we have to pick the first letter, then we have to pick the second letter, then we have to pick the third letter, followed next by the digits, and they said there's 3 digits, so we have to pick the first digit, the second digit, and the third digit. So picking the letters and the digits means 3 choices for the letters in a row, 3 choices for the digits in a row. So that's 6 different steps in the process. Picking the first letter, picking the second letter, picking the third letter, then pick the first digit, the second digit, followed by the third digit. So the entire process is broken down into these 6 separate steps. Now we just have to figure out the number of ways each of these steps occur as an individual, multiply them all together, and that will be the number of ways the entire process could occur. Now when they say we could pick from 3 letters, we take that to be the letters available in the English language. And there are 26 letters in the English language. So as we pick our first letter, I could pick from any of the 26 letters of the English language. Now in terms of picking the next letter, we need to ask ourselves, can I repeat digits? For instance, could I have the sequence AAA? It said repetition is allowed, so I could pick from the same 26 letters again because it's okay if I end up repeating the same letters. So there's 26 ways to pick the second letter. Okay, think to yourself, how many ways are there to pick the third letter since repetition is allowed? That would be 26. Now we need to pick the first digit. Now, in some problems, they tell you particularly what digits are you allowed to choose from. And if that's the case, definitely look at those and then count how many options are there available. But in this particular problem, they just said 3 digits. So unless specifically specified otherwise, if they just tell you pick from the digits, you're to assume that you could pick from the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that is in total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 options. So there's 10 possible digits that we could choose from. So the number of ways to pick the first digit is 10, and since I'm allowed to repeat, I could pick all 10 digits I can choose from for the second digit, along with the next one. Now, in order to figure out the number of ways the entire process could occur, because right now we've just done step by step, you multiply all these together. Now, this is going to be an extremely large number. Some of y'all's calculators won't even be able to calculate it. It will give you something in what we call scientific notation. So when the number of ways something could occur is very large, what we can do is instead of writing it out in scientific notation or a very large number with many, many digits, we can use exponents to say 26 multiplied by itself 3 times is written mathematically 26 cubed. Times 10 multiplied by itself 3 times is 10 cubed. Because repeated multiplication can be expressed as exponents. 10 times itself 3 times. 26 times itself 3 times. And that's how we go about this problem. For additional practice, let me now change the problem slightly, and let's see how that would change the way the problem solved and how many options would be available to us. The change that I want to introduce, and if you want, write this on a separate piece of paper, it's a new problem, is now repetition is not allowed. And that's the only change I'm going to make. It's still going to make a license plate made up of 3 letters followed by 3 numbers. But now we can't repeat, so I can no longer have the license plates that are like AAA 111. I could have the license plates that are like ABC 123. So any digit or letter that appears once can never occur in subsequent locations of the license plate. So keep in mind this is a completely new problem, and we're determining how many ways we could do the license plates with 3 letters and 3 numbers if we do not repeat any letters or digits. So take a moment to think to yourself, how many ways could we pick the first letter? if we're picking from the 26 letters of the English alphabet. There's 26 ways. Any of the 26 numbers we could pick first. Now keep in mind, in this problem that we're thinking about, of the 26 letters available, we have now used one of the 26 letters as our first digit. And since I cannot repeat digits, I no longer can use that digit again in subsequent choices. So since I've used up one of them, 26 minus the one I've used means there's only 25 letters available to choose as the second digit to avoid repetition. Okay, follow a similar train of thought and think, how many ways could you pick the third letter if we're avoiding repetition? Okay, originally there was 26 letters available. However, I've already used up one and then two of the 26 letters available. I can't use either of those two again, so 26 minus 2 leaves me with 24 options left. Okay, I'd encourage you to pause the video now and, thinking in similar patterns, figure out the number of ways you could pick the first digit, second digit, and third digit, keeping in mind that repetition is not allowed. And then unpause to check your work. So in the first digit, we kind of have a clean slate. We know there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are options. In all, that's 10 options available. So I could pick from any of these 10 options. However, once I've picked my first digit, whatever one of those 10 digits it becomes, that digit cannot be reused in the second or third digits. So I've used up one of the 10 options, which means there's only 9 available for the second digit. Now, in terms of thinking of the third digit, I can't use either of the two that I've used for the first or the second. So 2 of the 10 digits are off the table. That leaves only 8 digits remaining here. And for this particular problem, we would just leave this as our final answer. 26 times 25 times 24 times 10 times 9 times 8. It's a large enough number that it would either come out in your calculator in scientific notation or a number with many, many digits. So for very large results, just leave it in the multiplicative form. As you go about your homework problems in this section, always ask yourself, is repetition allowed or is it not? Because as you can see in these two examples that we just completed, the thought process will change if repetition is allowed or if it's not allowed. We have a 4-digit number is constructed using only the digits 1, 2, 3. So notice here they specifically told us you can only use these digits. So for this particular problem, 4 is not an option. Neither is 5, 6, 7, 8, 9, or 0. We can only use 1, 2, or 3. They ask us how many numbers are possible, key phrase, assuming repetition is allowed. Now the whole part of these problems in this section is being able to take an overall process and break it down into the correct number of individual steps. Then once you've broken it down to individual steps, figure out the number of ways each of those steps could occur, multiply all of that together, and that's the number of ways the process occurs. So the first key step that you must make as a student solving these problems is identifying for the described situation how many steps could I break it into. So I would encourage you to take a moment and pause the video now and reread the information given here and ask yourself, how many steps could I break this process into? How would I describe those verbally? And then, how many ways could each of those individual steps occur? After you've taken time to think about it and attempt it on your own, unpause the video to check your work. So our key phrase here is a 4-digit number. That means there's 4 different digits written together. So I've got something in the ones place, the tens place, the hundreds place, and the thousands place. So I like to write down these brackets to help me focus on each step. Again, they're just organizational, but I'm going to continue with that process. So I'm going to say this is my first digit. And I know since it's the fourth from the right, it would actually be the thousandths place. Next up is the second digit. Then I need to pick the third digit. And then I need to pick the fourth digit since it's a fourth digit number. Now, keeping in mind how this was phrased with what I've underlined in red, would this be an appropriate choice of a 4-digit number? Is this a possible example? No. The problem here lies in the fourth digit, 4. I was told I could only use the digits 1, 2, or 3. So of the digits available, there are 3 original digits available to use, 1, 2, or 3. I also know that repetition is allowed, so I could have the number 1, 1, 1, 1. Or I could have the number 1, 2, 2, 2. The key idea is I can repeat digits, but I can only work from the digits 1, 2, and 3. So how many ways could I pick the first digit? Well, I could use either 1, 2, or 3. That means there's 3 ways in all. So I put down 3 ways to pick the first digit. How many ways could I pick the second digit? Well, since repetition is allowed, I still have all the original 3 digits available to be used. So there's still 3 options for the second digit. Since repetition is allowed, there's 3 options for the third, 3 options for the fourth. Multiply that together. Now this is a small enough number that we could write it as either 3 multiplied by itself 4 times is 3 to the fourth. Type this into your calculator and you'll get this is equal to 81. So there are 81 ways to construct a 4-digit number that uses the digits 1, 2, and 3 where repetition is allowed. Now as a related problem, we're asked how many of these numbers are odd and less than 2,000. So let's think, what are some ways that we could go about solving this problem? I guess one way is I could write out all 81 4-digit numbers that are using the digits 1, 2, and 3 with repetition. And then from that list of 81 numbers, I could just X out anything that's even. I could X out anything that's greater than 2,000. And only the remaining digits should be counted, and that would be how many numbers from this group are odd and less than 2,000. However, that would be a very time-consuming process to first write out all 81 of these options and then X out anything that is not odd or not less than 2,000. Assuming we didn't make any mistakes, we would then have to count up the remaining options. So that is a possibility, but based on the amount of time it takes, it's not going to be a profitable one for us to go through. So instead, we want to really understand this descriptor of odd and less than 2,000. How can we make sense of this in terms of our 4-step process? Because we understand this breaking it up into separate steps. So we need to be able to phrase what does odd or less than 2,000 mean in terms of these 4 steps. Well, whenever you're trying to see if a number is less than 2,000, and for instance, I had these numbers written. What digit do you look at to see if a number is less than 2,000? Look at these 2, and what digit tells you whether it's less than 2,000 or greater than 2,000? Would y'all agree that that's what we are calling our first digit? If the number in the first digit's place is 2 or greater, the number is greater than 2,000. However, if the number in the first digit is less than 2, specifically in this example, the only number less than 2 that we're allowed is 1, the number's less than 2,000. So in order to get a number for our first digit less than 2000, the only one of the 3 digits we were allowed at the beginning that could be used is 1. So we have only one option here. Instead of the original 3, I could not choose 1, 2, or 3 anymore because choosing a 2 would make a number greater than 2000. Choosing a 3 would make something in the 3000s also greater than 2000s. I could only choose the digit 1 here in order to ensure that my overall number is less than 2000. At this point, I would encourage you to gauge how well you understand that thought process. And if it's a little shaky, go back in the video to where we first introduced this portion of the problem and then replay it. And take a moment to even pause the video and think about it. Definitely email me if you have questions. And once you feel confident about the idea that to be less than 2000 is a property of the first digit, then continue on with the rest of this problem solving. So we've been able to phrase in a counting-based argument what it means to be less than 2000. Next, let's focus on, based on our 4 digits that we count, which one of the 4 digits has the property that makes the problem odd. To help us see this, I'm going to write down a few different options of 4-digit numbers that fit our criteria of using digits 1, 2, and 3 that are specifically less than 2000. And I want you to focus on what property in those numbers makes the number odd. Look at these 8 4-digit numbers that I've listed, and then think about which one of these or which of these 8 numbers would be considered an odd number. What's considered the odd numbers? These 4. What is the property of these 4 that I've highlighted that makes them odd? The way you determine an odd number or an even number is always the last digit. A 4-digit number is odd if its last digit is odd. Similarly, a 4-digit number is even if its last digit is even. So when they say that we want an odd number, this means I must ensure the last digit is odd. Now we had 3 options to begin with that we could choose from, 1, 2, or 3. How many of these 3 options are odd? 1 and 3. So basically, if I want my 4-digit number to be odd, I cannot have a 2 as the last digit because that will make the 4-digit number even no matter what the earlier digits were. So when I'm thinking about this process, I've got my 2nd digit, I've got my 3rd digit, but in order to make sure the number's odd, I have to focus on the 4th digit. So as we said before, anything that involves special restrictions, deal with that first. We've already dealt with the 1st digit because it's what makes our number less than 2000. Now we're going to deal with the 4th digit because it's what makes our number odd. And I know in order for the thing to be odd, the last digit must be odd. Of the options available to us, how many of those are odd? Well, I could pick 1 or I could pick 3. That is 2 options. So there's 2 options here. And again, as you do these problems, keep in mind, I'm not saying that we choose the number 2, right? I'm saying there's 2 options. What are the 2 options? Either 1 or 3. Now with this in mind, we have now ensured that our number is odd. We've ensured that it's less than 2000. So there's no more restrictions that could be met, and that means we could choose anything that was originally acceptable to go in our 2nd or 3rd digit. So we were still okay with repetition. And in terms of the 2nd or 3rd digit, I could choose from either 1, 2, or 3. So there's 3 options for the 2nd digit, 3 options for the 3rd digit. The reason that we had special restrictions in our 1st and our 4th place is because those placeholders are what have to do with being less than 2000 and being odd. Any of the other digits just fit the original restrictions of using the digits 1, 2, or 3 and allowing repetition. And that's why we still had 3 options available here. So multiply all these together and that gives you the overall amount, 1 times 3 times 3 times 2 is 18. So there's 18 of the original 81 four-digit numbers using 1, 2, or 3 in repetition, which happen to be odd and less than 2,000. So whenever we're asked how many of the numbers that we were thinking about fit particular criteria, you need to be able to rephrase that criteria in terms of a restriction on one of the steps of the original process. And as just an introduction to the idea, if they ask you to make the number even, in order to be an even number, the last digit must be an even number. So if a problem asks you to make the number even, they're really giving you a restriction on the last digit, that it must be even. Similarly, if you're asked to make a number odd, then its last digit must be odd. Similarly, if they asked for a number to be less than 7,000, and I just picked 7,000 as an example, this principle applies in general if you think about it similarly for different restrictions. That's really a criteria on the first digit. In order for a number to be less than 7,000, its first digit must be less than 7. So the allowable options are 1, 2, 3, 4, 5, or 6 for the first digit. Now, I'd like to point out here why I'm not including 0. Why is 0 not in this list? Because 0 is less than 7. The reason 0 is not in this list is consider the number 0, 1, 2, 3. Now, technically there are 4 digits written, but isn't this really the same thing as 123? It's just written in a very weird way, 0, 1, 2, 3. The reason we don't allow 0 in the options here to construct our 4-digit number less than 7,000 is because if you have a 0 in the first place, it's actually not a 4-digit number or whatever digit you're trying to create. If there's a 0 in the first place, it actually makes the number that you're representing 1 less than you intended. So 0 is not in this list, not because we wanted to have a number less than 7,000, but because we wanted to ensure the exact amount of digits mentioned in the problem. So keep these 3 criteria in mind, and they will be helpful as you go through different problems to realize the phrase of the number must be even is a restriction on the last digit. The phrase the number must be odd is a restriction on the last digit. Saying a number must be less than or greater than some value means that's a restriction on the first digit, and you just have to think through how many ways can I still meet that restriction with the original restrictions of the problem. We describe n factorial, where n is a number, positive number. This expression has the implied meaning that whatever number n is, n read factorial, that's how we read the exclamation point, says you take that first number that you started with, n, and then you multiply down through the preceding integers. So if we started at n, then we next multiply by n minus 1. Then we next multiply by n minus 2, and we continue this pattern until we get to 2, and then finally until we get to 1. Now I wrote this in a generalized way with n factorial so that it would make sense with any number, but particularly as we're introducing a new idea, I think it could be helpful to see this with some actual values. So let's look first at 5 factorial. As I'm reading this, I would read the number 5, and then in this area of mathematics, if you see the exclamation symbol, we're not dealing with 5 anymore, but instead we're dealing with 5 factorial. And the implied meaning of 5 factorial is that I take the digit 5, which I started with, and then I multiply down through the preceding integers until I get to 1. So the preceding integer before 5 was 4, followed by multiplying by 3, then multiplying by 2, then multiplying by 1. And if you go through multiplying all the preceding integers, you will eventually end up at 1, and you always stop after you multiply by 1. So let's calculate exactly what is 5 factorial. It's 5 times 4 times 3 times 2 times 1. So 5 factorial since it always follows this rule, will always be equal to 120. Next, let's take a moment and calculate 4 factorial. I'll give you a moment to write that on your paper. So at 4 factorial, 4 exclamation mark, we know we start at the integer 4, and then I multiply through the preceding integers. So then times 3, then times 2, finally times 1. Once I get to multiplying by 1, I know that I stop. Type that into the calculator, and we get that 4 factorial represents the number 24. Now take a moment to read this expression. We should see this as 5 factorial, which is some value. We actually just calculated that it's 120. Then divided by 4 factorial, which we know is 24. So whenever we're dealing with calculations that involve factorial, you have 2 approaches. First, you could calculate them separately as we did here and then divide it. So 120 divided by 24. And we get the value 5. Another way that you could do it, if you don't want to calculate both, is write out what 5 factorial and 4 factorial is. So our other method could be to say 5 factorial is 5 times 4 times 3 times 2 times 1. I need to divide that by 4 factorial, but 4 factorial is 4 times 3 times 2 times 1. And an important mathematical rule to keep in mind is if we have a fraction that has the same thing in the top and the bottom, and there's just multiplication in between, then you can cancel common terms. So the 4 above cancels with the 4 below, the 3 above cancels with the 3 below, 2 above cancels with the 2 below, 1 above cancels with the 1 below, So the only thing left is this 5 term. And that's why 5 factorial divided by 4 factorial is just 5. So we've seen the example of how to deal with a factorial in general. So for instance, as just a quick review, write out what 8 factorial would be. Here we would start at 8 and multiply down through the preceding integers. And then if we type this into our calculator correctly, we'll get a value. We also saw how to do some calculations of different mathematical operations that happen to have factorials as part of it. Now, keeping in mind this last example, notice when we had 5 factorial divided by 4 factorial, when we wrote out the 5 factorial and we wrote out the 4 factorial, they shared all the same common terms except for the first digit 5. Let's expand this reasoning in this particular case to what I have written here, which is the general case, and I'm going to try to highlight why this pattern matches. It begins by saying in factorial. And then it divides by n minus 1. Notice the n minus 1 is in parentheses, and then we apply the factorial. So in our previous example, the n is the 5, and the 5 minus 1 is the 4. So we see this actually is a particular case of this formula. And in the particular case, the 5 factorial divided by 4 factorial just ended up being the 5. So with that in mind, could you predict in general if we ever have n factorial divided by n minus 1, then apply the factorial, what will that always simplify to? It'll simplify to n. And the reason is, if we write out n factorial, by definition that's n times n minus 1 times n minus 2, all the way down until we get to 2 times 1. Similarly, n minus 1 factorial starts at n minus 1. Now, n minus 1 is actually n minus 2. And then we continue multiplying through the preceding integers till we get to 2 until we get to 1. However, all of this taken together is exactly n minus 1 factorial, as is all of this. And whenever something's above in the fraction and below and there's only multiplication in between, those will cancel perfectly with each other, so that all we're left with is the n. So this is a helpful shortcut. So let's apply that in this case. 7 factorial divided by 6 factorial. This fits the pattern because I have an integer factorial, and then I'm dividing it by the preceding integer's factorial. We know by the formula this will simplify to just be 7. And if we weren't sure about using the formula, then just write out what 7 factorial is. Write out what 6 factorial is. And see that as we discussed before, these terms would cancel with each other. Let's continue to practice working with factorials. So we have 4 examples. In the first, we're asked to calculate 3, and then remember you read the exclamation mark as factorial. 3 factorial means take the value 3, and then multiply it by its preceding integers until you get to 1. 3 times 2 times 1 is 6. Now, before we do the next 2, focus on the difference in how example 2 is written and example 4 is written. Look carefully at the details. An important thing that we need to read in terms of the details shown on example 2 is notice that the 6 divided by 3 is in parentheses, and in mathematics you simplify what's inside parentheses first. This means I need to take 6 and divide it by 3 first before I ever apply the factorial symbol. So what's in parentheses comes first. Now 6 divided by 3 is 2. So this means I need to rewrite the inside of the parentheses as a 2 before I apply the factorial. Now 2 factorial means take 2, multiply it by the preceding integers. There's only 1, 2 times 1. So example 2 has value 2, whereas example 4 there is no parentheses, so I should instead read this as 6 factorial that is then divided by 3 factorial. Now I'd encourage you to attempt example 4 here, pause the video and work on this on your own, and then unpause to check your work. There's a few approaches here. Remember that we can write out what 6 factorial is, figure out what 3 factorial is, and then divide them. I personally prefer to just write it out and then cancel any common terms, and then that makes my calculation simpler. So I've written out what 6 factorial is, I've written out what 3 factorial is, and I cancel the commonly appearing terms, so that all I'm left with after cancellation is 6 times 5 times 4, which is 120. Now in our final example, it says take 6 factorial and then subtract 3 factorial. So in order to do this, I must calculate 6 factorial first. Calculate 3 factorial, we already know 3 factorial 6. So let's off to the side calculate 6 factorial. And we get 720. Here might be a helpful hint. Notice when I write out 6 factorial, the past 5 terms is really 5 factorial. So it's 6 times 5 factorial. We know from a previous example 5 factorial was 120. So I could figure this out maybe a little more quickly if I knew 5 factorial was 120, because then it's just 6 times 5 factorial, and we'd get 720. So I have 720 minus 3 factorial is 6. 6 factorial became our 720. 3 factorial became 6. And then when we subtract those, we get 714. So this has just been some practice with finding basic factorials and then dealing with mathematical operations that include factorials. Let's now introduce the idea of permutations. We'll begin with this example. Suppose that Alan, Cassie, Maggie, Seth, and Roger are friends who would like to take a photograph with only 3 of the 5 possible friends in it. So of the friends listed, Alan, Cassie, Maggie, Seth, and Roger, not everybody will be in the photograph. They are curious that if only 3 individuals at a time were in the picture, how many different ways could they end up taking the picture? Now we can solve this just based on what we know so far. In a previous video, we learned about the fundamental counting principle, which said if you can break up a task into subsequent parts, then you can figure out how many ways each part could occur, and then the total way the process would occur is all of those pieces ways multiplied together. So the way I'm going to think about this is imagine we had our 5 friends off to the side. So here's our 5 friends. They're waiting off to the side in order to decide how to stand in our photograph of only 3 friends. Now, does it make sense that if I have a photograph with Seth, Cassie, and Maggie, if I have Cassie first, farthest to the left, then Maggie in the middle, and Seth farthest to the right, that would be a different photograph than if instead Seth was farthest to the left, Maggie stayed in the middle, but now Cassie was farthest to the right. So an important thing to note in this example, even though it didn't come out and say order matters, we can think based on the situation that yes, the order that people stand up for a photograph is going to make a different picture, so it's implied that order matters. So going forward, if you deal with the problem, even if it doesn't specifically mention whether order matters or not, you need to think through the situation and think in that case, would order matter? And in here, it most definitely would, because changing the order of how they're standing up will make a visually different photograph. Now this is just 2 examples, 2 possible ways the friends could choose to stand up together. And I need to find all possible ways. So what happens is I have the 5 friends here, and each photograph is basically determined by who stands in the first position, who stands in the middle position, and then who stands in the third or the furthest right position. So I can think of this problem as overall a process with 3 separate pieces. I need to figure out who's going to stand at the farthest left, who will stand at the middle, and who will stand at the farthest right or the third position. Now, as we had all 5 friends here, we need to pick one of them to go here. Now, at this time, how many friends are available? 5. So we have 5 options of who will take the first place. Now, does it make sense once one of these 5 friends has stood here, even though we don't know which friend took that place, we do know one of the 5 friends is now standing here. So there's realistically only 4 friends remaining who could now take the second place, because of course a person couldn't stand here and then duplicate themselves and stand here. So we also realize we cannot repeat. So when trying to determine who could go to the middle position, we can't have the person who's already here, so there's now only 4 possibilities. And then by similar reasoning, the last position, 2 people have already stood up, so there's only 3 remaining people that we could choose from. So this is the number of ways each step could occur, so the number of ways the entire process could occur could be found by multiplying those. And we would get 60 as our possibility. There are 60 different ways we could create a photograph from the 5 friends if only 3 of the friends are in the photo. Now, so far, this is not new reasoning. We learned this kind of reasoning in our previous video. The reason we bring this up in our permutation section is that we could have also solved this problem through something called a permutation. And once we know how the permutation formula works, it's actually a nice shortcut. So let's see our permutation formula. So a permutation tells the number of possibilities for an arrangement from in total objects into a smaller collection of R objects, and one thing we need to note here is in a specific order. So for permutations, we need to say order matters and we can't repeat. That's the thing that you need to link. When can you use permutations? When order doesn't matter and you can't repeat the objects. So in this formula, n is the total number of objects you start with. And then just like in our last example, we started with 5 friends, but only 3 were in the photograph. We chose a smaller amount to be in the photograph. We start with n objects, and then we reduce that and only have a smaller number of R objects that we're arranging. So n is the bigger number, R is the smaller number. Once you've identified those two numbers, we write the expression mathematically as the permutation of n objects from n objects to R objects is equal to, and then we see this formula, n factorial, calculate that separately, divided by parentheses n minus R factorial. And remember, when parentheses are involved, we have to subtract first before we apply the factorial symbol. So this is an important formula. If you don't have these notes with you, then write this formula down on whatever scratch paper you have, because we will need to reference it in our future examples. Let's see why this idea of permutation will apply to our next example. Suppose we've been asked to judge an art contest that has 15 entries in all. How many ways could we assign first, second, and third place? Now, before we get started and focused on the formula, let's instead make sure we understand why in this situation order matters and we can't repeat the objects. The way we're going to think about this problem is, since we're asked to select first, second, and third place, the first artwork that we pick will be assigned first place. The second artwork that we pick will be assigned second place. The third artwork that we pick will be assigned third place. So the order that we pick it follows along with the order in the ranking. So order matters because if I had artwork A picked first, then artwork B, and then artwork C, the way we're thinking about this problem, that naturally means A gets first place, B gets second, C gets third. But if instead I had B picked first, then C, and then A, by how our labeling works, oh, I messed up the colors. No, I didn't. We'll go back to that. B, C, A. B would be applied first place because it was picked first. C would be applied second place. It was picked second. A would pick third place. Notice in both of these options, I've used the same 3 letters, A, B, C, but because order matters, if I picked A first, that's a situation where A would get first place. Whereas in this situation, A was picked last, so it got third place. So hopefully with this, we can see it doesn't just matter that we pick 3 objects, it matters the order in which we pick them, because that will say which is assigned first, second, or third place. So that's why order matters here. Similarly, this example helps us see why repetitions are not allowed. If I had A, that would mean A as an artwork got first place, second place, and third place, which just isn't possible. Something needs to hold first place, something needs to hold second, something needs to hold third. The ranking makes it where you can't choose the same piece of art for all 3 awards. So that's an example why repetitions are not allowed. So we know why order matters. We know why repetitions are not allowed. Two key features that we need to focus on once we realize we can use permutation is what is the value in and what is the value of r in this particular problem. Remember, n is the total number of objects that we start with, and then r is the number of smaller amount of objects that we're looking to arrange in a particular order. So read through our problem and think, what would you find n to be and what would you find r to be? We started with 15 entries in all, so n is 15. We only want 3 entries ranked first, second, and third, so r is 3. And since order matters, our formula is the permutation of the total number of objects 15, selecting only 3 of those objects. We're going to write out the formula word by word and then we'll calculate it. It's the first number factorial, so 15 factorial, divided by parentheses 15 minus 3, close parentheses. We must write the parentheses here, they're essential, then factorial. Now 15 minus 3 is another way of writing 12. So this becomes 15 factorial over 12 factorial. Now we're going to write this out completely by definition, and then hopefully as we do so, y'all will see a shortcut of how to calculate this more efficiently. Let's illustrate that. So we'll begin by just writing out the expression 15 factorial is 15 times 14 times 13 times 12 times 11, all the way down to the preceding integers till we get to 1. This is just the definition of factorial. And then 12 factorial is a similar pattern, except it starts at 12 and multiplies down through the preceding integers until we get to 1. And then what do we notice about this divided by this? It's the exact same thing, and we know in a fraction if you've got the exact same thing above, the exact same thing below, and it's only multiplication in between, then those will cancel, and this will become just 15 times 14 times 13, which is 2,730. Now this is no surprise that so many terms canceled, because if you ever have a larger number factorial divided by a smaller number factorial, eventually they'll start repeating the exact same terms. Specifically, they'll always start repeating at the smaller numbers factorial, because 12 factorial would always have 12 multiplied by 11 all the way down to 1. And 15 factorial has that plus these extra terms at the front. So everything in common will cancel. So a way to think about a particular formula is if we have n factorial divided by n minus r factorial, it will always be the n times n minus 1 until you get to the term right before our n minus 1. So n minus r, I wrote that as n minus r plus 1. Now this is hard to see in symbols. We're much better just thinking about it in an example. So if I had 15 factorial divided by 12 factorial, I know that after cancellation, all that I'll be left with is the 15, the 14, and the 13. All values 12 and under will cancel because they'll appear at the top and the bottom. So if this shortcut makes sense to you, or if you think you've got it, pause and think about it a bit more, and you'll find it useful. It's a great way to simplify your calculations. If it doesn't make sense to you, that's okay too. You can always write out the factorials by definition and then see what cancels. Either way, you're going to get to the same answer if you've done it correctly. Our next example has 10 students are to be chosen from a class of 30 and then lined up for a photograph. How many such photographs can be taken? Now first ask yourself, in this example, does the order that the students line up for the photograph matter? If you had the same 10 students and you changed their order around, would it make a new photograph? And the answer to that is yes, order does matter, because even if I had the same 10 students, if they're in a different orientation, it makes a different photograph. We could visually tell them apart. Next, ask yourself, could I repeat the students? Could I have the same student standing in the first place and the second place and the third place? No, each individual could only stand in at most one place. So no repetition. Whenever I think about permutations, I always ask myself a few basic questions. First, order matters. That's important. Next, I can't repeat. The final question is, do I go from a bigger group to a smaller subgroup that I'm selecting? And in this case, yes, we started at 30 people. And then we want to winnow this down until there's only 10 people chosen. So we've gone from our bigger group to our smaller group. So because all of these criteria are met, we know we're dealing with the permutation. And we know our permutation formula is the permutation of the total n objects into a smaller collection of r objects is always n factorial divided by n minus r factorial. That's our formula from above. So all that's left is to identify what is n, what is r, and then correctly apply the formula and simplify our answer. N is always the larger starting number, so it's looking at the permutation of 30 people, selecting only 10 of them. And then take a moment to write out the formula if you know that n is 30, r is 10. I recommend you pause the video, write out the formula, and then unpause. So the formula says it should be the total number first, 30 factorial, over, now I do parentheses, 30 minus 10, close parentheses, must have the parentheses, factorial. Now 30 minus 10 is actually 20, so this is 30 factorial over 20 factorial. Now I could write out what 30 factorial is. I'm going to say it briefly. It would be 30 times 29 times 28 times 27 times 26 times 25 times 24 times all the way down until we get to finally times 2 times 1. 20 factorial would be 20 times 19 times 18 times 17 times 16, etc., all the way till we get to 2 times 1. As we're thinking about that, we notice once both the values start hitting 20 and below, those are going to cancel out. So this would simplify to just 30 times 29 times 28 times 27 times 26 times 25, I need more space, times 24 times 23 times 22 times 21. And then once they hit 20, they would start canceling above and below, and this is why we're only left with this. Now, I think this would be a very large number. Whenever the answer's extremely large like this, you do not have to calculate it further. You could have left your answer choice like here or here, or you could write it out like this, or you could multiply it all together and get the value. It's just for the extra large numbers, it's not particularly necessary. We just need to get to either of these answers. So far, we've introduced the idea of permutation. We've done a few examples involving permutations. Let's now look at the related topic of combinations. So the way you're going to differentiate between when you should use a permutation and when you should use a combination is that in permutations, order matters and we cannot repeat. In combinations, we similarly cannot repeat, but the difference is that combinations are when order does not matter. So if order doesn't matter, use combinations. If order does matter, use permutations. Now, the formula for combination is the combination of n objects, that's our largest number. Notice how it appears in the formula. Selecting down to a smaller group of r of those things, so r is a smaller number, is going to be equal to n factorial, all divided by the product of r factorial, so that's the smaller number, multiplied by in the denominator, parentheses, n minus r factorial. Now, just so we can see these compared side by side, this is the formula for permutation that we learned earlier. So the main difference between the permutation formula and the combination formula is the combination formula has this extra term in the denominator where we have the same term below, but then we multiply it by the new factor of r factorial. So keep in mind the difference. Permutations are when order matters, whereas combinations are when order does not matter. So next I have an example of just some different types of problems we could see, and then I have them classified whether they should be a permutation or a combination. Keep in mind for combinations, if you see words like committees or group or team, those are indications you should use combination, because in a committee, group, or team, the order that you're in the team does not matter. It just matters that you're there. You're in the committee, you're in the group, you're in the team. There's no order implied. However, with permutation, it's going to be things like, for instance, picking first, second, and third place winners. The order that it's picked indicates a different place, which means it's different. As we've seen before, arranging people for photographs because the order that they're in the photograph matters. If instead of just picking a team, we were picking members on the team, so picking a captain, picking a pitcher, picking a shortstop, that would be a permutation type problem because the order that they're picked gives them a different position on the team. So if there's ever an idea that the order that I pick something gives it a different meaning, that's going to be a permutation. Whereas if all that matters is that I pick them to be there, but the order that I pick them does not matter, that would be a combination. So these are some options. Take a moment if you'd like to pause the video and read through it, but these are examples of when a permutation should be applied, when a combination. The basic idea is order doesn't matter for combinations. Whereas in a permutation, order definitely matters. Now, it just happens that many of our examples will discuss cards because it's an easy reference. There's different descriptions. It just works very nicely for counting problems. However, I know not everybody might have played a card game, so if you're not familiar with cards, then this table will be helpful for you. First of all, it shows that we have 4 suits. These are our club suits, diamonds, hearts, and spades. So for a normal type of card deck, we have 4 suits. They're all listed here. Notice I've got 2 suits that are black colored, clubs and spades. 2 suits that are red colored, diamonds and hearts. And this is important because sometimes a problem will say from the red cards, sometimes from the black cards. Now each suit has 13 cards. So let's count the number of clubs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So every suit has the same 13 cards, just with a different symbol attached to them. And in particular, every suit has 3 face cards. The face cards are the jack, king, and queen of each suit. So if there's 3 face cards in each of the 4 suits, how many total face cards are there? 3, 6, 9, 12. So keep in mind there's 12 total face cards. How many total cards are there in all? Well, each of the suits has 13 cards, so there's 13, 26, 13 more is 39, plus 13 more is 52. So there's 52 cards in all, split into 4 suits. Every suit has 13 cards, and then every suit has 3 face cards, the jack, king, and queen of that suit. So mark this page in your notes. You might find it helpful later on to flip back to it as we deal with problems that say so many cards of this suit, so many face cards, etc. We have an example involving cards coming up next. It tells us that a common card game is poker, and in poker, 5 cards are dealt to each player from a standard deck. So whenever we say a standard deck, we're just saying there's nothing wrong with it. It's the 4 suits. each suit has the 13 expected cards. And we know the standard deck in all has 52 cards of all together. Now, whenever we talk about a hand of cards, that's just a phrase in terms of cards. That's going to be when you're dealt, you have card 1, card 2, card 3, card 4, and card 5. So imagine you already have these 5 cards in your hand. Would it matter if you as an individual, if they're already in your hand, move this last card and switch places with the first card? It wouldn't matter. You would have the same 5 cards in your hand, just in a different arranged order. So to visualize this, imagine this was one of the hands that I got dealt: a 10 of diamonds, 5 of hearts, ace of hearts, 8 of hearts, 4 of hearts. This is what I'm holding in my hand right now. And if I move this 4 of hearts in front of the 10 of diamonds, it does not change the fact that my cards are still 4 of hearts, 10 of diamonds, 5 of hearts, ace of hearts, 8 of hearts. So in a hand of cards, once they're in your hand, the order no longer matters. Now, just so we can visualize this, let me deal again. And this is my new hand of cards. So I see I have a 8 of hearts, 9 of hearts, king of clubs, 2 of clubs, 5 of clubs. Again, once these 5 cards are in my hand, if I switch their order internally in my hand, changing the order does not change the 5 cards that I still hold. So to answer this question, if the cards are already in your hand, does the order matter? No. Order does not matter, because I still have the same 5 cards. And since order does not matter, that makes me think of combination formula when dealing with cards, because the order doesn't matter. So next we're asked, how many different 5 cards hands are possible? Well, the idea is if we're going to use combinations, we have to know what is the starting total number of cards I could draw from, and then from that larger number, I want to select only 5 of them. So the smaller number is definitely 5, so R is 5. Think about what was the total number of cards that I could have drawn from. That would be 52, because at the beginning, I could have chosen from any of the cards in the deck. There was 52 options to select from. I'm only selecting 5, and order doesn't matter, so that means I use the combination formula. The combination from 52 objects down to just 5. We know the formula, if we look at our previous formula, it was n factorial over r factorial times n minus r factorial, where n is 52, so this is 52 factorial over r factorial, which is 5 factorial, times 52 minus 5, close parentheses, then apply the factorial. I'll need to simplify this. 52 minus 5 is 47, so this becomes 52 factorial over 5 factorial times 47 factorial. Now, since both of these are very large number factorial, that's a good thing because much of what occurs at the top will then eventually cancel with what's at the bottom. Because remember, what is factorial? 52 factorial would be 52 times 51 times 50 times 49 times 48 times 47 times 46, all the way down to times 2 times 1. I definitely do not want to write all of that out because I'm going to end up canceling most of it, because right below is 47 factorial, which means 47 times 46 times 45 all the way down to 2 times 1. The only thing that won't cancel between these two is the starting term of 52 from the top, 51, 50, 49, 48, because once we get to 47, it will cancel perfectly with what's below. Now, 5 factorial, we need to rewrite this. So at the top, we have 52 times 51 times 50 times 49 times 48. That's what did not cancel. The bottom canceled perfectly. The 47 factorial canceled with the 47 factorial at the top. And then we're left with 5 factorial below. Now, with practice, you're going to associate 5 factorial as 120. So if you know that, you could have just written divided by 120 below. And I think this will be small enough that we can calculate this out. So I have 52 times 51 times 50 times 49 times 48. So I'll write that carefully. Divided by 5 times 4 times 3 times 2 times 1 I know is 120. I'll divide those. And we get 2,598,960. So if I'm dealing from a 52 card deck and I'm dealing 5 cards, there's 2,598,960 different ways I could deal a 5 card hand from those 52 cards. Now, if you think you're getting the hang of when to use permutations, when to use combinations, when to use fundamental counting principle, I'd encourage you to do these next 3 examples on your own. Pause the video, attempt them on your own, and then unpause to check your work. If you'd still like to see these ideas kind of guided through, then just watch the video without pausing, and we'll work through them right now. So in our first example, it says, how many 4-digit numbers are there? And let's just read through the next examples too so we can get an idea of their differences. And then we'll come back to this. In the next example, it says, how many ways can 3 of 8 people line up at a ticket counter? So there's 8 people in all, but we only want 3 of them to line up. And then the final one is, how many ways can a committee of 3 be selected from a group of 12? Now, one thing I hope we notice in both of the last 2 examples is notice we started with more people, 8 people in this group, 12 people in this group, and we wanted to get to a smaller collection in the first example to 3, in the second example also 3. So both of these had the idea of a bigger group selecting down to a smaller group, except they differed in that the second example, if people are lining up, does the phrase line up, does it imply that order matters or doesn't matter? I would say order matters when we're lining up, because the person who lines up first would get help first versus the person who lines up second and the person who lines up third. They're not just collecting together in a group, there's a meaning to their order. So here I would say order matters. Whereas in this next one, if we're just selecting a committee, we know all that matters is that we're on the committee. There's no implied order about this person was picked first for the committee, so they have some meaning. No, it's just if you're in the committee, you're in the committee. So here we would say order does not matter. So both of these examples have the idea of bigger group to smaller group, which generally bigger to smaller means either permutation or combination. And then the way you choose between permutation and combination is you ask yourself, does order matter or not? Because if I'm going from bigger group to smaller group, which I am in this second and third example, but if order matters, then I have to use permutations. However, if I'm going from bigger group to smaller group as I am in the third example, but order does not matter, then I use combinations. And our first example is in a completely different category, because notice it's not saying select from this bigger group a smaller subsection. It's just saying how many 4-digit numbers are there. This is our fundamental counting principle, because in the fundamental counting principle, if you're making a 4-digit number, you have to pick the first place to the left, which is the thousands place. Then you have to pick the hundreds place, then the tens place, and then the ones place. So it's the idea of picking a 4-digit number is picking 4 places, figure out how to do each of those separately, and then multiply it together gives you the entire way to do the whole process. And this particular example was the topic of our previous video, whereas example 2 and 3 are what we're talking about in this video, permutations and combinations. So that's an overview of the different strategies we use for each of these. Let's focus now on the first example. Remember when it says how many 4-digit numbers, unless they specify otherwise, the digits that we're allowed to use are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, since we're not otherwise restricted. Now, I'd like you to consider, could I put any of these digits in the first digit to the left, the thousands place? Consider, could any of those 10 digits go here? Consider if I wrote down this possibility. Does this meet my criteria of being a 4-digit number? I have 4 numbers written, but it's not really a 4-digit number. This is a 3-digit number in disguise, right? 0, 1, 2, 3 is 123. So if you're asked a 4-digit number, remember that 0 cannot come first. Because if 0 comes first, you're not really writing a 4-digit number, you're writing a 3-digit number in disguise. So in terms of how many options could go in the first place, you could use 1, 2, 3, 4, 5, 6, 7, 8, 9. You could use 9 possibilities, but we could not have 0. Now here they did not say repetition wasn't allowed, so it's implied that it's okay because I could 33333 is definitely a 4-digit number. So now that we've dealt with the first decimal place, which we had to avoid 0, there's no reason why I couldn't have 0 in the subsequent locations, because it's no longer an issue of being 4 digits or not. So for the second decimal place, I could use 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So there's 10 possibilities. And then since I can repeat, there's 10 possibilities for the third place and 10 possibilities for the second place. So that would be 9 times 10 times 10 times 10, or 9,000 possible 4-digit numbers. So we've previously discussed why we would use permutation for this next example, combinations for the last ones. I'm going to write down the permutation and combination formula. So once you know you're using permutations, always copy down the formula so it's visible. Similarly, I know in the last one I'll use combination, so I'll write down the combination formula. If I write this down in general, I'll probably be much more consistent in finding the correct answer. So I have the general formula. Now in particular for our second example, I started with 8 objects. I wanted to arrange 3 of them when order mattered. So I had 8, that's my total number. I'm selecting 3. So to follow my formula, it would be 8 factorial over 8 minus 3 factorial. Now, I think we've done enough examples that you might have noticed, oh, 8 minus 3 is just 5, so this is going to be 5 factorial. You could have definitely in your head subtracted 8 minus 3 and then just written 5 factorial. Feel free to do that, or you could write it out and then in a next step simplify it. Now 8 factorial divided by 5 factorial, I could write out 8 factorial as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I could write out 5 factorial as 5 times 4 times 3 times 2 times 1. And then I could realize, oh, they both have 5 times 4 times 3 times 2 times 1 as part of it. Those terms would cancel and I'd only be left with 8 times 7 times 6 because all later terms were in above and below, so they'd cancel. Now 8 times 7 times 6 is 336. So there's 336 different ways for 3 of the 8 people to line up at a ticket counter. Next, our final example, because it's a committee and order doesn't matter in committees, we're going from a larger group to a smaller group. We know we use the combination formula. Here in particular, it's the combination from 12 as the larger group to only 3. And our formula says you take the factorial over 3 factorial times 12 minus 3 factorial. Now this would be 12 factorial over 3 factorial times 9 factorial. Now I'm just going to write all of these out just to help people visualize. If you're comfortable saying, oh, with the 12 factorial over the 9 factorial, all that would left after you cancel is 12 times 11 times 10, keep going with your work. I'm going to write that out so we can see. 12 factorial is 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. And then 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. We see that we have the same items above and below the 9 factorial appears as a portion to each. Anything that's the same above and below, and there's only multiplication, will cancel perfectly to where we're only left with the 12 times 11 times 10 at the top over the 3 times 2 times 1 that didn't get canceled. Now this is going to simplify nicely. Let's calculate the top. 12 times 11 times 10. That's 1320. 3 times 2 times 1 is 6. Divide that by 6. And we get our answer of 220. Is what the whole calculation simplifies to. So there's 220 ways that we could take from 12 individuals and select 3 of them when order does not matter. So a good way to assess your progress with what we've learned in this video and the previous video is, are you comfortable with why we did the fundamental counting principle in this example, why we use permutations here, and why we use combinations here? Because each problem is slightly different and it was necessary to use a different approach in order to solve it. In the first example, if we can ever break up a process into separate pieces, then you can find out the number of ways you would deal with each piece, multiply it all together, and that's the way you would deal with the total. If instead we're going from a bigger group to a smaller group and order matters, we use the permutation formula. Contrasted with if we're going from a bigger group to a smaller group but order does not matter, then we use the combination formula. Let's continue working with these formulas. It says, how many ways are there to choose from a team of 7 from a class of 20 students in order to make a basketball team? Now, one thing I first notice is we've got the idea that we're choosing from a larger group. We have 20 students to start with, and then we want to select to a smaller group of only 7. So this is the idea of bigger to smaller. I know that that fits in a certain pattern. If I've got a bigger group to a smaller group, I then need to ask myself, does order matter or not? Because if order doesn't matter, it's combination. If order does matter, it's permutation. So think of the way this is phrased. We're choosing people for a team. Does the order matter when we're choosing a team, or does it just matter that the 7 people are on a team regardless of the order that they're picked? In terms of a team, order does not matter. So will we use combination or permutation? Since order does not matter, we are going to use our combination formula. If I need to, I reference back in my notes and I write down the general formula. The combination from n total objects into r smaller is n factorial over r factorial times n minus r factorial. Now for our particular example, n is 20. We started with the larger collection of 20 students. We're selecting only 7, so that's 20 factorial over 7 factorial times 20 minus 7 factorial. The bottom would simplify. 20 minus 7 is 13. And then here we simplify. I know that top is 20 factorial is going to be 20 times 19 times 18, etc., all the way down to 2 times 1. And it has most in common with the 13 factorial. There will be a lot of cancellations here. In fact, these two will cancel together until all that we're left with at the top was 20 times 19 times 18 times 17 times 16 times 15 times 14. 13 and below is shared, so they cancel. The bottom was 7 times 6 times 5 times 4 times 3 times 2 times 1. This term, the 13 factorial, canceled with the 13 factorial that was part of the 20. If we'd like, we could just type the top into our calculator, divide it by the bottom. However, if you'd like to simplify further, 7 goes into 14 2 times. 5 goes into 20 4 times. Let's see what else we could do. 6 goes into 18 3 times. Now this is not necessary. You could have just typed it in as it is. This might make my calculations a bit easier though. 16 and 4 goes into 16 4 times. And then finally I think I could get 3 goes into 15 5 times. So this will give me a smaller number where I have 4 times 19 times 3 times 17 times 4 times 5 times 2. Everything at the bottom canceled except 2 times 1. So that's going to be 155,040 divided by 2. So if we start with 20 students and we only want to select 7 and order doesn't matter, there would actually be 77,520 ways to complete that. Next, we're asked how many poker hands consist of 5 red cards only. Now, we introduced a little bit about cards and the idea that a poker hand has 5 cards. So whenever we read poker hands, we need to remember that there's 5 cards in a poker hand, and it was dealt from a standard 52 card deck. So we started with 52 cards, we dealt only 5, and then remember, once it's in your hand, order does not matter. So with that in mind, bigger idea to smaller, we're dealing with combinations, but actually I need to specify a little bit more. In the 52 cards, there's all 4 suits, right? If you look back at our previous diagram, you'd see spades, diamonds, hearts, and then clubs. But this problem specifically says we only want red cards. So in actuality, we did not want to be dealt with from the clubs or the spades. So since it says red cards only, we did not start with 52 options because that means we could have got one of the spades or one of the clubs in our hand. We only wanted red cards. In fact, we were only dealing with the 2 red card suits. There's 13 cards in each suit. So we had the 13 diamonds and the 13 hearts. So together we were dealing with 26 possible cards as our total because we were okay with anything from the diamonds, anything from the hearts. From those 26, we're only choosing 5. So we know our general combination formula. We always write that down off to the side. 1, it's helpful just to have this visually close by for reference. 2, the more times you write it, the easier it will be to remember the formula. So for our particular example, we were starting with 26 cards because we're only using red cards. That's why we're using 26 instead of 52. We're selecting only 5. The formula tells me it should be 26 factorial over 5 factorial times 26 minus 5, then factorial. Now this can simplify. Okay, 26 minus 5 is 21 factorial. And the 26 factorial and the 21, a lot's going to cancel there. Because remember, what is 26 factorial? It's 26 times 25 times 24 times 23 times 22 times 21 times 20 times 19, etc. down to times 2 times 1. 21 factorial starts at 21 times 20 times 19 times 18 all the way down to 2 times 1. So whenever you cancel what would occur from the 26 factorial and the 21 factorial, all that you'd be left with is from the bigger one, you had the 26 that didn't cancel, the 25, the 24, need a bit more space, the 23, the 22, and then once you got to 21, it started canceling with what was at the bottom. So we've dealt with this, divided by, I guess they didn't cancel perfectly. I want to watch that notation. The 21 got canceled with what was at the top. That's why we didn't have anything from 21 below there. But we still had the 5 factorial, which is 5 times 4 times 3 times 2 times 1. We also know that 5 factorial is 120. You could replace this with 120. Let's calculate the top. You could also do some cancellation if you want, like I did in the previous example. You could say 5 goes into 25 5 times, 4 goes into 24 6 times, etc. But if that's too complicated, just calculate what the top is and divide that by what the bottom is. Here you want to make sure you don't make an error typing something in incorrectly for sure. Five times 4 times 3 times 2 times 1 is 120. And we get there 65,780 possible ways to get a 5-card hand from only the red suits.